Hello everyone, today we will be continuing combinational logic circuit, and first of all we need to learn some specific terms related to the minimization of Boolean expressions. First term is literal cost. Literal cost literally means the number of variables you can see in expression. For example, in this expression there are total of 8 literals. Let us count. This B is 1, D is 1, A is 1, B complement is another, C is 1, A is 1, C complement is 1, and D complement is 1. By adding the number of all these complemented and non-complemented variables, we find the literal cost. Similarly, in another example, the second one, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 literals. In examination, you might be asked to minimize or simplify the expressions up to 4 literals or something like that, so you need to learn that term. Now, let us continue with the topic, and one of the simplest combinational circuit is half adder. In half adder circuit, two binary bits are added together. We can see an example, 0 plus 0 is 0. Though those two variables can be any of the combination, either it can be 0, 0 or 0, 1 or 1, 0 or 1, 1. So let us add 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2. 2 can be represented as 1, 0. So 1 will be carry and 0 will be our sum. That's why we get output as in the form of sum and carry. We have already studied that the first step of designing a combinational circuit is understanding the problem. So here the problem is to add two binary bits. The first step is to identify what the circuit is supposed to do and determine the number of inputs and output required for that circuit. Let us move towards the second step. In previous step, we concluded that there should be two inputs, and let us name it with any of the variable names. For example, I have given A and B for the two inputs. Similarly, you can use X, Y or UV, any variable of your choice. And we have also found that there will be two outputs, and the outputs are going to be sum and carry. So I'll be using variable S to represent the sum and C out to represent the carry. That is output of the half adder circuit. So step 2 is also complete. Now we should move towards constructing a truth table. Truth table is basically a table showing all possible input combinations and output combinations that the circuit is going to produce. Here, A and B are our inputs, and sum and carry are going to be our output, which is also shown in step 2 as the block diagram. And while making block diagram, it is a standard practice to write the name of the circuit inside the block and represent inputs and output as shown in the given figure. In the truth table, A and B are the inputs, and the combination can be either 0, 0, 0, 1, 1, 0 or 1, 1. So here are total of 4 combinations. Number of combinations can also be found by using a formula 2 to the power n. Here we have n equals to 2, which means number of input equals to 2. So 2 to the power n equals to 2 to the power 2, which equals to 4. That's why we have 4 combinations. Now let us add individual inputs. Let us start with 0, 0. Sum of 0, 0 is 0, and we do not have carry during the addition of 0 and 0. In second combination, there are 0 and 1. While adding 0 and 1, the sum is 1, and we don't have carry, so we write 0. In the third combination of inputs, we have 1 and 0. Sum of 1 and 0 is 1, and we have 0 as the carry. In last combination, the numbers are 1 and 1. We have already found that sum of 1 and 1 is 1, 0, where this 1 is carry and 0 is our sum. In binary, 1, 0 means 2, right? We can also perform, this is binary and this one is decimal. This one is decimal, 1 plus 1 is decimal 2, and in binary we represent it 1, 0. So we have finally found our truth table, from which we need to derive the equations for sum and carry, equations for both of the outputs. For simpler circuits like this, we can directly write the equation, but for more complicated ones, we need to use complex techniques like Karnoff map or McCloskey law to find the output equation. Okay, then let's proceed with the fourth step, in which we have to find the equations. Use K-map to get simplified expressions if the expression is long or the problem is too complex. If the truth table has a small number of outputs having 1, then directly we can write the SOP form. Let us be clear about this. Let's proceed with the expression for sum. We can write sum equals, now you have to see in this column of sum, where the output is high, and we can find two rows where the output for the sum is high, and the first one corresponds to the value 0 for A, which means A complement, and 1 for B, which can be written as B. And in another row, the combination of A and B is A because of this 1 and B complement because of this 0. Okay, so finally we need to add these two products because it is a sum of products or min terms, as we have already studied in previous lectures. Similarly, for calculating the carry, our expression is going to be, we have to find 1 or output where the output is high. There is only one output that is high, and for which the inputs are 1 and 1 for A and B. So carry is equals to AB. This is our Boolean expressions for sum and carry. In step 5, from the Boolean expression derived in previous step, we need to draw a circuit diagram. It is also known as logical circuit diagram. For that, we need to take two inputs A and B, and we have to generate two outputs, sum and carry. First of all, let's calculate the sum. The sum is written as A complement plus AB plus AB complement, which can also be written as A XOR of B. So we can directly make an XOR gate, exclusive OR gate, and its output is going to be our sum. Similarly, the carry is going to be A and B, as we can see in the equation of carry. The sum is going to be A XOR B, and carry is going to be AB. We can clearly see in the figure the sum is A XOR B, because the inputs here are A and B. The output is going to be A XOR B. Okay, similarly, the carry is going to be A and B. This is our final circuit for the half adder. And step 4, we need to verify the circuit if it works for the all combination of inputs or not. At first, you check for 0 0. If the sum of 0 0 is 0 or not, the XOR of 0 and 0 is always 0, because we also know the property of XOR as output of XOR is only high if only one of the inputs are high. If both the inputs are low or both the inputs are high, the output is going to be low. That's why for 0 0, output is also 0, which is true. For 0 1, the output is also 1. For 1 0, the output is 1. And for 1 1, the output is 0, sum is 0. Similarly, you can check for the carry and validate if the circuit is wrong or not. Thank you for watching till the end. We will be learning about other combinational circuits in following lectures. Thank you.